My dear students, let me welcome you all to a new edition of the physics. In this edition, we'll learn about Kirchhoff's law. We cannot use Ohm's law to solve problems of circuits when the circuits contain two or more batteries, when the two batteries are connected in parallel. Okay, so we have to find something else to solve these problems. If you want to learn how to solve these problems, we should learn about Kirchhoff's law. So let's get started. Kirchhoff's laws. Kirchhoff current law. It states that the sum of the currents arriving at any junction point, we call it node. So the sum of the currents arriving at any junction point in a circuit must equal the sum of the currents leaving that point. So in front of you at junction point A in the diagram, in the circuit, we can say I minus I1 minus I2 equals 0. That's to say I equals I1 plus I2. Currents arriving equals the currents leaving the node. Second law, it is Kirchhoff's voltage law. It states that the total voltage applied to any closed circuit path. Closed circuit path, we call it loop. The total voltage applied to any closed circuit path is always equal to the sum of the voltage drops across the individual parts of the path. Sum of voltages aiding current flow equal sum of voltages opposing current flow. This is another way to express this law. That's to say the algebraic sum of all voltages encountered in any loop equals 0. Okay, Kirchhoff voltage law can be applied to loops anywhere in any type of circuit. Okay, we'll use the laws to, first of all, to solve a simple one. So the first problem here, okay, says use Kirchhoff's law to find the value of I, I1, and I2. In front of you, we've got a circuit. Yes, it contains two cells. 10-volt cell of internal resistance R1, which is equal to 1 ohm, and 1 volt, yes, cell of internal resistance 0.5. And we've got two resistors, 6 and 2. This is very simple one, and it can be solved by using Ohm's law, as long as the two cells are connecting in series. Okay, but we'll use Kirchhoff also. Okay. So by applying Kirchhoff voltage law, on loop A, B, C, D, E, A, we can say 10 minus 1x, okay, 1x, x is the current passing through the main circuit. Y is the current passing through the 6 ohm resistor. So the current passing through the 2 ohm resistor must be x minus y. Okay? So by applying the voltage law, we can say 10 minus 1x minus 1 minus 0.5x minus 6y equals 0. Okay? It follows 9 minus 1.5x minus 6y equals 0. So we can find y in terms of x. Y equals 9 minus 1.5x over 6. Okay, And also by applying Kirchhoff voltage law on loop A, B, C, F, G, D, E, A, we can say 10 minus 1x minus 1 minus 0.5x minus 2, between two brackets x minus y, it is equal to 0. This can be arranged in the following. 9 minus 3.5x plus 2y equals 0. This is the second equation. Substituting for y, we'll be able to determine the value of x. X was found to be 3 amperes. Y equals 0.75 ampere. So x minus y is 2.25 ampere. Second problem. Okay, in front of you, we've got a circuit. Your attention now. We've got two batteries that are connected, yes, parallel to each other. In this case, Ohm's law cannot be used. We have to use, yes, Kirchhoff's law to calculate the value of the currents. So we've got a circuit that consists of 100 volt and 10 ohm resistor, another 6 ohm connected in series. And we've got 4 ohm and another battery 60 volt and resistor of 12 ohm. We want you to use Kirchhoff's law to calculate the value of the current in each resistor. Okay, so let the current passing through the main circuit issuing out from the 100 volt is X. The current entering the 4 ohm branch is Y, so the current through the 12 ohm will be X minus Y. It is shown in front of you. And we'll apply Kirchhoff's voltage law on loop A, C, B, A. So we can say 100 minus 4y minus 16x equals 0. So 100 minus 16x equals minus 4y. So y equals 25 minus 4x. This is the first equation. By applying Kirchhoff, yes, voltage law on loop ACEDBA, we can say 100 minus 12 between two brackets x minus y plus 60 minus 16x equals 0. So 100 minus 28x plus 12y equals 0. This is the second equation. Substituting for y, we'll be able to determine the values of x. It is 6.05 ampere, y, which is 0.78 ampere, x minus y 5.2635 ampere. Third problem. Okay, in front of you, we've got 3 batteries. Okay, one which is 4 volt battery, 12 volt battery, and battery of unknown EMF, VB. Okay, and we've got 3 resistors, 2 ohm, 4 ohm, and 6 ohm. An ammeter that reads half ampere. And we want you to use Kirchhoff's law to calculate the value of the EMF of the battery. As I said, the meter reads half ampere in the direction shown in the figure. Okay, by applying Kirchhoff voltage law on loop A, B, C, D, A, we can say 12 minus 4x minus VB minus 0.5 times 2 equals 0. So 11 minus 4x equals VB. This is the first equation. By applying Kirchhoff voltage law on loop G, A, B, C, D, E, G, we can say 4 minus 6 between two brackets 0.5 minus x, okay, minus VB minus 0.5 times 2 equals 0. So VB equals 6x. Substituting for VB, x equals 1.1 ampere. So it's all easy for you to determine the value of the battery. it is equal to 6x, so 6 times 1.1, it is 6.6 volt. And now let's, solve some verbal questions. First question, give reason for. The resistance of a conductor increases as its length increases. As the length of the conductor increases, we want you to justify this. The resistance increases with increasing the length of the conductor of the wire because electrons collide with an increasing number of atoms when we increase the length. Also, this is very important. A lone wire can be regarded as a group of wires, group of resistances connected in series, so their resistances are added together. Each piece of a long wire is regarded as a resistance connected in series to the rest of the wires. Okay, this was about the first give reason. Second give reason, the resistance of a conductor increases as its thickness decreases. Okay, as the thickness of a wire decreases, there are fewer spaces between atoms in the cross-section through which electrons can travel. In addition, we can also say a thick wire can be regarded as a group of resistances connected in parallel. It can be regarded as a group of thin wires connected in parallel, so their equivalent resistance decreases. Third give reason for, the resistivity of a material is regarded as a physical property, characteristic property, but the resistance cannot be regarded so. Okay, this is very important and interesting. Resistivity of a material, unlike its resistance, is a constant at any given temperature. Remember, resistivity in general depends on kind of material and temperature. So at any given temperature, it is a constant and is independent of the dimensions. Independent of the dimensions means independent of a length and the cross-section area of the wire. So let me say it again. Resistivity of a material, unlike its resistance, is a constant at any given temperature and is independent of the dimensions, length and cross-section area of a sample of that material. But resistance depends on length and area. Last give reason, electrical conductivity of a pure metal is high. Why? Because there are many free electrons that are not bound to any particular atom. So a metal contains free electrons. That's why its conductivity is high. Okay, because there are many free electrons that are not bound to any particular atom within the material. Another type of questions. Prove that the electric energy supplied or converted by a device is determined from the relation VIT, where V is the potential difference, I is the current intensity, T is the time. Okay, it's all easy, and it is the first proof in your curriculum. Since potential difference between 2 points is determined from the expression W, energy over charge, W over Q, so energy denoted by W is the product of V and Q. Also, current intensity is determined from the expression Q over T. So current intensity, as I said, equals Q over T, so charge equals IT. From 1 and 2, from the first equation, which was W equals VQ. Second, Q equals IT. We can say W equals VIT. Okay, and we've got another question. Prove that the electric power dissipated in a resistor can be found using the following expressions. Power can be determined by the formula IV. It can be determined by the formula I squared R or V squared over R. Okay, once again, as I said, potential difference equals W over Q. So W equals VQ. Current intensity equals charge, amount of the charge, over time. So amount of the charge Q equals IT. From 1 and 2 we can say electric energy equals VIT. But power equals energy over time. So power equals VIT over T. T will be crossed out. So the formula here that determines power equals VI. And from Ohm's law, okay, V equals IR. Okay, so I equals V over R, substituting, yes, in equation 3, so power equals I squared R, and substituting for the current, we'll obtain power equals V squared over R. Another question. 3 identical lamps are connected across a battery of negligible internal resistance. Okay, once in series and at another time in parallel. 3 identical lamps are connected across a battery of negligible internal resistance in series and then in parallel. Prove that the ratio of the powers dissipated in the two cases is 1 over 9. Okay, we'll take it one by one. Okay, starting, yes, with the connection where they are connected in series. Starting with the series connection. R equivalent equals 3R. Okay, in front of you we've got a circuit. And what about the current through the battery? It is VB over 3R. And the power is determined from the expression I squared R equivalent. So it is equal to I1 squared R equivalent, substituting for the current. So it is equal to VB over 3R, okay, squared times 3R. So the power is equal to VB squared over 3R. This was about when connecting the 3 lamps in series. When connecting them in parallel, R equivalent in this case equals R over 3. The power is determined by, as I said, VB squared over R equivalent. So it is equal to 3 VB squared over R. When comparing the first power to the second, VB squared over 3R times R over 3 VB squared, it will be 1 over 9. And now we want to make a comparison, yes, between specific resistance, which is resistivity, and resistance. Okay, so compare between specific resistance and resistance. Okay, first point of difference is definition. Resistivity of a material is the resistance of a wire made of that material. 1 meter in length and 1 meter squared in cross-sectional area at that temperature. So this was about the definition of resistivity. It is the resistance of a material of that resistance of a wire made of that material, 1 meter in length, 1 meter squared in cross-sectional area. Definition of resistance is opposition to the flow of electric current. Okay, second point of difference is the measuring unit. Yes, measuring unit of a specific resistance is ohm meter, and unit of resistance is ohm. And third point of difference, what about the factors affecting each one of them? Factors affecting the resistivity is two factors only, kind of material and temperature. But factors affecting resistance are four factors: length, cross-sectional area, kind of material, and temperature. Last point of difference is being a characteristic property or not. Specific resistance is regarded as, yes, a characteristic physical property, as it doesn't depend on the dimensions of the wire. But resistance cannot be regarded so, as it depends on the dimension of the wire. Another type of questions, what's meant by? What's meant by the ratio of the potential difference across the terminals of a conductor to the current passing through the conductor equals 10 volt over ampere. Ratio between voltage and current intensity, it is resistance. Of course, it means that the resistance of that conductor, yes, must be equal to 10 ohms. What's meant by the resistance of a wire? 1 meter in length, having a cross-sectional area 1 meter squared at 20 Celsius, is 1.7 times 10 power negative 8 ohm. Okay, when length is 1 meter, area 1 meter squared, resistance will be equal to resistivity. So the resistivity of the material of that wire at 20 Celsius is 1.7 times 10 to the power of negative 8 ohm meter. What's meant by the electrical conductivity of copper at 20 Celsius is 5.6 times 10 to the power of 7 ohm negative 1 meter negative 1. It's all right. Conductivity is given. We can convert it into resistivity. Resistivity is the reciprocal of conductivity. Resistivity is the reciprocal of conductivity. So it is equal to 1 over 5.6 times 10 power 7. It is 1.7 times 10 power negative 8 ohm meter. And now we can say the resistance of a piece of copper of length 1 meter, cross-section area 1 meter squared at 20 Celsius is 1.7 times 10 to the power of negative 8 ohm. What's meant by the electric current intensity through a wire is 5 amperes. Current intensity flowing through a wire equals 5 amperes. It means the rate of flow of electricity is 5 coulombs per second. Each second, a quantity of electricity of 5 coulombs passes. What's meant by the potential difference between 2 points is 10 volts. It means a work of 10 joules is required to transfer, yes, unit charge to transfer 1 coulomb between these 2 points. What's meant by the resistance of a conductor is 3 ohm. It means the ratio of the voltage applied across the terminals of the conductor to the current flowing, ratio between voltage and current, is 3 volt over ampere. Another type of questions. Use the following units to form 3 groups of equivalent units. Then mention the physical quantity measured in using the units of each group. The units are joule per coulomb, watt second, volt times coulomb, watt, ampere times ohm, ampere squared ohm, watt ampere negative 1, volt, joule second negative 1, meter squared kilogram second negative 2. Okay? We want you to make 3 groups of equivalent units. Okay, first group is joule per coulomb is equivalent to ampere times ohm. Joule per coulomb is volt. Ampere times ohm also is volt. And volt is given clear cut and also watt per ampere. Watt ampere -1. They are all units of potential difference. This is the first group. What about the second group? The second group are units of electrical energy. Okay, what are these units? Yes, it is watt times second. Watt times second is joule. Okay. Also, volt times coulomb and meter squared kilogram second -2. So let me say them again. Watt second, volt times coulomb, meter squared kilogram second -2. They are all equivalent units. They are units of electrical energy. And third and final group is, yes, units of power. Okay, we've got watt. What is a unit of power? Joule per second, which is joule second -1. Ampere squared times ohm. They are all units of power. Another type of question, it is choose. Okay. The equivalent resistance of a group of equal resistances, okay, they are equal resistances, connected in series, are equivalent equals 100. When they are connected in parallel, their equivalent resistance equals 4. Okay, we want you to choose. The value of each one of them is 100, 50, 20 ohms. Let me say it again. The equivalent resistance of a group of equal resistances when connected in series equals 100 ohm. So 100 equals NR. Their equivalent resistance when connected in parallel is 4 ohms. So R over N equals 4. And by solving these two problems, the value of each one of them will be equal to, yes, 20. Very interesting choice here we've got. We've got a ring here in front of you. The equivalent resistance between the ends of the ends A and B of a ring is 20 ohm. So 20 is the resistance of the entire ring. Okay. The effective resistance between 2 points D and E at the ends of a diameter on the ring is 10, 5, 7.5. No correct answer. Okay, if the current is passed at a point D and leaves at point E, and these 2 points are on the diameter of the ring, the resistance is decreased, yes, 4 times. So it was 20. So the right answer is 5 ohms. This is very important. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.